Hello, Dr. J here. I'm going to do the integration property of the Laplace transform. I'm going to give you a pictorial description before I go through the derivation. The derivation is kind of messy because you have to recall in your calculus class the integration by parts formula. So here's a pictorial depiction of the integration property. Start off with the input f of t. We're going to describe this in the time domain first and then in the Laplace domain. So we start off with the input f of t, go through some operation. In this case, we go through an integral. Then out pops the integral of our input. So our output is just the integration of our input. In the Laplace domain, we have f of t, and its Laplace description is f of s. Feeds the input as before, but we're going to show in this video that the integration property can be reduced to 1 over s. And the output is just the product of your input Laplace transform, the Laplace transform of the input multiplied by the Laplace transform of the integration function, which is 1 over s. So the output is simply, in the Laplace domain, f of s divided by s. So you could see here, this in the Laplace domain is just an algebraic approach corresponding to the time domain approach of using calculus techniques. And we'll show that you can get the same result either going through the time domain and through the Laplace domain. But you could see here in the Laplace domain, once you know what the corresponding Laplace transforms, the output is just simply an algebraic multiplication of the input multiplied by the Laplace transform of the integral, which is 1 over s. Please don't get confused with the input of the step, which also has a Laplace transform domain description of 1 over s, because that's for an input. But for an operation, 1 over s is the integral or operation. So what we want is to find the Laplace transform of this operation here. And so this is equivalent, the Laplace transform of this integral operation on f of t is equivalent to f of s divided by s. That's what we want to prove. And we're going to use the integration by parts formula. First, we apply the definition of the Laplace transform, which is, we take this function here, which is an integral of f of t, alright, which forms another function, multiplied by our definition e to the minus st dt, and that's our Laplace domain description integrating from 0 to infinity. So all this is our definition of our Laplace transform, where our function is the integral of f of t dt, or f of tau d tau as a dummy variable when we're integrating from 0 to t. When we do that, I highlighted here, we'll define this portion, the integral from 0 to t, f of tau d tau, as y, and that e to the minus st dt as dx. Here's our integration by parts formula. So there's our y dx on the left side, and on the right side we're gonna substitute x and y after we find it. In this case, our dy and x, after we subtract it right here, we have dy is just simply, when you take the differential in this highlighted area, f of tau d tau. Taking the integral of this differential, we get x equals minus e to the minus st divided by s. So now we got y dx, dy, and x for this integration by parts formula. And we're just going to basically substitute all these things that I defined here, 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 and here, and just substitute it in the formula. So on the next slide, we're going to substitute those variables. Here's our x term, here's our y term, and after you manipulate x dy, we see that we have 1 over s term that came from our x term, And then our e to the minus st came from our x term as well. And our dy term came from f of t dt. But we're going to integrate from 0 to infinity. Okay, but what we note here is our definition of a Laplace transform. F of t e to the minus st dt integrating from 0 to infinity is our definition of the Laplace transform. Now let's take a look at the upper and lower limits in this first term here. We could see here when we substitute t equal to infinity, this goes to 0. And that when we substitute the lower limit 0 to 0, this integral is 0. So this first term here is 0. And what we're left with the second term is f of s divided by s. So all of the first term goes away, and what we're left here is f of s divided by s. So the Laplace transform of an integral of a function is f of s of that function, the Laplace transform of that function, divided by s. So in other words, what we did is replace the integration operation with 1 over s in the Laplace domain. And that's it with the integration property for the Laplace transform. In the next video, I'm going to show you the Laplace transform of a ramp using the integration property. We're going to show that the Laplace transform f of t equals t equal u times t is equal to r of t, and that its Laplace transform is 1 over s squared. Why don't you apply the Laplace transform of the integration property and find the Laplace transform of the ramp and see if you can get 1 over s squared. Till then, signing off.